Okay, the midterm solutions are on the web now. I uploaded them in the class along with the questions. So if you have any questions about the solutions, then we can discuss it some other lecture, but not today. But if you have any particular question you have about the midterm and the solutions now, anything that is kind of puzzling you, or about any of the things we had done up to now. Okay. Now, if you remember, on last week we had started discussing the harmonic oscillator. We said that if we define these two operators, A and A dagger, then the Hamiltonian, we could write it in the form A dagger, A plus 1/2 times h bar omega. And these operators had these nice commutators. If you take the commutator of h with A, this was proportional to A with a negative proportionality constant. And H, the commutator with A dagger, was proportional to A dagger with a positive proportionality constant. And we use these facts to show that if you have any energy eigenstate, if you act on this energy eigenstate with A, it is still an energy eigenstate, but it has a different energy eigenvalue, and that its energy eigenvalue was reduced by h bar omega. And if you do the same thing with A dagger, if you act with A dagger on an energy eigenkette, then you obtain another energy eigenkette, but the energy of these energy eigenkette is increased by h bar omega. Well, sometimes these A and A daggers, they are called ladder operators, meaning that they increase or decrease the corresponding eigenvalue. Sometimes they are called annihilation creation operators, in the sense that if you think of these energy eigenstates as states containing packs of energy h bar omega, A just annihilates one of these packs, energy packs, and A dagger creates one of these energy packs of h bar omega. So it increases and decreases. It creates or annihilates energy packs in the given state. And then what we had done was we also said that, well, the expectation value of the Hamiltonian, since it's just the linear superposition of p squared and x squared with positive constants, the expectation value in any state has to be larger than 0. But you say A decreases energy eigenvalue by h bar omega if A acting on this energy eigenstate is non-zero. So at some point we should stop lowering the energy eigenvalue. And it tells us that there should be a ground state which we call 0. A acting on this ground state should be 0. Now, once we have this ground state, we can build energy eigenstates, let's say E, the Hamiltonian, acting on A dagger 0. Well, we know that A dagger increases the energy eigenvalue by 1. Or let's start with H acting on this ground state. Now H, which was h bar omega, A dagger A plus 1/2. If we act with H on the ground state, this is h bar omega, A dagger A plus 1/2 acting on the ground state. But you see, A acting on the ground state is 0. So this first term doesn't contribute, so we end up having the energy eigenvalue of this ground state h bar omega over 2, non-zero. Well, in the midterm questions, you were supposed to drive this ground state energy using the energy uncertainty relation. So basically, at least in the harmonic oscillator, the energy uncertainty relation allows you to determine the exact ground state. And then when you have A dagger acting on the ground state, it would increase the energy eigenvalue by h bar omega. So initially it was h bar omega over 2, this is the ground state energy, but a dagger acting on any energy eigenstate basically increases the energy eigenvalue by h bar omega. So this just becomes h bar omega plus h bar omega over 2, a dagger acting on the ground state. And similarly, a dagger acting on the ground state n times, well, each a dagger will give you another energy eigenstate whose energy is higher by h bar omega. We have n of them. So the energy eigenvalue of this state will be n times h bar omega plus h bar omega over 2 to the power n acting on the ground state. And we can also write this as n plus 1 over 2 h bar omega acting on a dagger to the power n 0. And we also labeled this state a dagger acting up to the power n acting on the ground state. Let us just call them n with some tilde. Tilde meaning that we will see in a moment that these states are not normalized. And we will obtain the normalized states. Now this is what we had done up to this point. Now any questions up to here about the harmonic oscillator? Okay, so let me define this operator n also. A dagger A. Now we had already seen that H acting on n tilde, this is nothing but h bar omega n plus 1 over 2 n tilde. So H is nothing but, in terms of this n operator, Hamiltonian is nothing but h bar omega, this n operator plus 1/2. So this, since we already know this n tilde is an eigenstate of the Hamiltonian, it should also be an it should also be an eigenstate of this operator n. Basically h and n, they are the same operator up to a proportionality constant and the constant factor 1/2. If one is diagonalized, the other is automatically diagonalized. So n acting on this n tilde state is nothing but n multiplied with the n tilde state. Now let's look at this one. N tilde, this non-normalized states. N operator in between and n tilde. This should be equal to n tilde n tilde. This is n tilde. N operator is nothing but a dagger A. N tilde. This is equal to n tilde n tilde. Well, you see a dagger A is just a dagger plus a dagger A minus a dagger. This is a dagger plus the commutator of a dagger and A. Well, we had already calculated this commutator. That commutator is nothing but minus 1. So n times the inner product of n tilde is equal to n tilde a dagger minus 1 n tilde. So n, the inner product of n tilde, is nothing but, let me write that in this form. n tilde a dagger, a tilde, n tilde, minus n tilde, n tilde. By our definition, this state, or this state, is nothing but n tilde plus 1. You see, n tilde is n is basically the number of a dagger operators acting on my state. That is how I define those n tilde states. N tilde is the number of a dagger operators acting on the ground state. So this state n tilde ket contains n a dagger operators acting on the ground state. But now I am acting with one more. So that is n plus 1 dagger operators acting on the ground state. And so what I obtain at the end, n plus 1 tilde, n plus 1 tilde, this is equal to n plus 1, the inner product of the n tilde state. So basically this tells me how a dagger operator changes the normalization of my states. So let me start with the ground state. I will define the ground state to be properly normalized. Let me put the tildes. So the ground state is properly normalized. That's my choice. Well, since it's properly normalized, I will just define the zero state as the zero tilde state. So up to this point, I didn't really worry about the normalization. My states were not properly normalized a priori. So that's why I'm putting the tilde. But since I can choose the normalization of this ground state arbitrarily, you see, I'm defining all the other states using the ground state. So I'm free to choose the normalization of my ground state, but not the normalization of the other states. These tilde states, their normalization is fixed by the normalization of the ground state. So I choose my ground state to be properly normalized. So 1 tilde state is just look at this relation we have derived. Instead of n, I can choose the 0. If n is 0, this is nothing but 0, 0, which is 1. So the 1 state is just also 1 tilde state. They are also properly normalized. Let me look at the normalization of the second state. If you look again at the relation in the rectangle, you will see that if for n is equal to 1, the left-hand side becomes the 2, 2 state, the right-hand side becomes the 2, 1, 1 state. So basically, the 2, 2 state is not properly normalized, but I can normalize it, and so the 2 state will be just 1 over 2, square root of 2 tilde state. Well, I can just continue like this. Just in the relation in the rectangle, choose n is equal to 2. So I will get 3 times 2 tilde state. So this just tells me that the 3 tilde state, I should choose it as 1 over square root of 3, square root of 2 times this is the 3 state. And I can just go on like this. And at the end of the day, I see that the normalized energy eigenstate will be just 1 over square root of n factorial a dagger to the power n acting on the ground state. This is my energy eigenstate. Properly normalized. Well, a dagger acting on n is now 1 over square root of n factorial a dagger to the power n plus 1 acting on the ground state, which is 1 over square root of n plus 1 factorial multiplied by square root of n plus 1 a dagger to the power n plus 1 0. But you see this combination over here is just what I call properly normalized n plus 1. And A acting on n. Now let's try to calculate A acting on n. This will be equal to 1 over square root of n factorial a dagger to the power n acting on the ground state. This I can write as 1 over square root of n factorial times a dagger acting on the nth state minus a dagger acting on the nth state. No, sorry, let me write it in this way. Minus a dagger to the power n multiplied with a acting on the ground state. Well, you see the second term that I added just gives me 0 because A acting on the ground state is 0. So that's why I just added a 0 over there. But you see this term over there is nothing but the commutator of A and A dagger to the power n. Now let's see what that commutator is. We already know that a dagger is just 1. This is what we had already derived before. Well, let's look at a dagger squared. This is equal to a dagger plus a dagger a dagger. Well, this commutator is 1. So a dagger squared is just twice a dagger. Well, let's continue. Let's try to see some pattern so we can generalize it to an arbitrary power of a dagger. A dagger cubed. This is equal to a dagger multiplied with a dagger squared. This is equal to a dagger squared plus a dagger squared. Well, this is 1. This we had already calculated, that is twice a dagger. So a dagger cubed commutator is just 3 a dagger squared. Do you see some kind of a pattern? Well, you see, if you start from the first one, this is nothing but the derivative of a dagger with respect to a dagger. This is the derivative of a dagger squared with respect to a dagger. This is derivative of a dagger cubed with respect to a dagger. Well, this is basically similar to what we had done in the commutator of x and p and a function of p, or p and any function of x. The claim is that a dagger to the power n will also be derivative with respect to a dagger of a dagger to the power n. That is n times a dagger to the power n minus 1. So let's see whether this is true or not. So what we had done up to now is, well, let's just assume that a dagger to the power n minus 1 is equal to n minus 1 times a dagger to the power n minus 2. Well, this is definitely true for n is equal to 1. It is definitely true for n is equal to 2. It is definitely true for n is equal to 3. We had explicitly proven, shown it over here. Now we will do induction. So we will say that if it is true for any integer, any given integer, then it is also true for the next integer. That is what we will try to prove. Are you familiar with induction? Yeah, it's basically the same thing. So you prove that something is true for 1, you prove the same thing is true for 2, you prove it for 3. Well, in fact, if one of them is enough. Then what you prove is, assuming it is true up to a given integer, then you prove that it is true for the next integer. So that's basically the trick. Since it's true for the next integer, since it is true for 1, it should be true for 2. Since it's true for 2, it should be true for 3. Since it's true for 3, it should be true for 4. So it's true for all integers. This is the idea of induction. So what I had done is, for 1, my claim is definitely true. This claim is definitely, n is equal to 1, it is definitely true because a commutator with 1 is 0. For n is equal to 2, it's also definitely true. Now let's prove it for the a dagger to the power n. Well, this is a dagger times a dagger to the power n minus 1. This is a commutator with a dagger to the power n minus 1 plus a dagger to the power n minus 1 commutator. This we had already calculated that it is 1. This we had already assumed that it is equal to n minus 1 times a dagger to the n minus 2. So if you just sum them up, it just becomes n times a dagger to the power n minus 1. And by induction, it is true for all integers. Well, we basically needed it to calculate what the a acting on n is. This is equal to 1 over square root of n factorial. Well, that commutator is just n times a dagger to the power n minus 1 acting on 0. This whole thing is just square root of n minus 1 factorial multiply this n minus 1 ket. So a acting on n is just n over square root of n minus 1, or this is square root of n minus 1. So what we have, a acting on n is square root of n minus 1, and a dagger acting on n is square root of n plus 1, n plus 1. For me, it was always easy to remember these factors as they are the square root of the numbers that are larger. So you see a dagger acting on n, a dagger increases n by 1, so it's n plus 1. The larger among these two numbers is n plus 1, so the overall factor is square root of n plus 1. If you look at this one, a acting on any ket lowers the energy, so it should be the n minus 1 ket, and the larger between n and n minus 1 is n, so it's square root of n. That is just kind of a trick that I use to remember whether it's square root of n minus 1, or square root of n plus 1. Well, these basically define how A and A dagger acts on my states. So, and this is all I need to calculate the matrix element of anything I want. Now we will do some exercises. Now let's try to calculate the matrix element of X between the energy eigenkets N and M. For example, if I want to form the matrix representation of the position operator, these are the matrix elements. Well, first let's remember what were the definitions of A and A dagger in terms of X and P. So these were the definitions. Those are the things that I will always need. Well, you see, if you just sum A and A dagger, what you would get is 1 over square root of h power omega square root of 2m times omega x. This is equal to square root of 2m omega over h power times x, or x is equal to square root of h power over 2m omega times A plus A dagger. Let us also calculate P. Well, A minus A dagger, if you just look at the difference, then the x terms will just cancel each other. This will be equal to 1 over square root of h power omega multiplied by 2I over square root of 2mp. This is equal to 2I, or I over I times square root of 2 over h power omega m p or p would be equal to square root of 2 over m omega h bar A minus A dagger. No, it's the other way around. H bar omega m over 2. This is my P. Over I. Well, x and p are just like the real and the imaginary parts of these operators, A and A dagger, basically. So let me just write them on a single line. This is x. And this is our P, the momentum. Let's calculate their matrix elements now. M, X, N. This is equal to square root of H bar over 2M omega and A plus A dagger M square root of h power over 2m omega n. Well, A acting on m will lower the index by 1, lower the energy by 1 package. It's m minus 1. The proportionality factor will be square root of m. Plus A dagger will increase it by 1. Proportionality constant being square root of m plus 1. So this matrix element is nothing but h power over 2m omega square root of m Kronecker delta n m minus 1 plus square root of m plus 1 Kronecker delta n m plus 1. So this is not a diagonal matrix, but the only non-zero elements are the elements just above the diagonal and just below the diagonal.
What is in secret?
These ones. Well, I mean, this one, not much really. But let's look at this one. This is just 0. The diagonal elements are 0. So this basically tells me that the average of the position is 0. It basically means that in an energy eigenstate, the oscillator is likely to be found at positive positions as negative positions. So this is not really the state that we observe in practical application. I mean, when you look at an oscillator, what you would see is just the oscillator just moves to plus x, to minus x, to plus x, and the minus x. So we will see the states that closely resemble our observed states in a moment. Let us look at the matrix elements of P in general. Well, this will be equal to square root of h bar m omega over 2 times minus I n a minus a dagger m minus I square root of h bar omega m over 2 n m minus 1 square root of m minus square root of m plus 1 m plus 1. So this will be npm minus I square root of h bar omega m over 2 square root of m Kronecker delta n m minus 1 minus square root of m plus 1 Kronecker delta n m plus 1. Again, it's not a diagonal matrix. The only non-zero elements are just the line above the diagonal and the line below the diagonal. And again, if you look at a particular energy eigenket, the expectation value of P in that eigenket, this is again 0. Now these are kind of boring states, let's say. Now let us look at the energy uncertainty relation. So to calculate the energy uncertainty relation, we first need to determine this one in an energy eigenket. N delta x squared n, but we had already shown that this is n x squared n minus n x n squared. Well, this is already 0. So we only have to calculate the expectation value of x squared. Well, x is already given by, let me just write the coefficient, overall coefficient outside, h bar over 2m omega, and a plus a dagger squared, and this is equal to h bar over 2m omega, and a squared plus a dagger squared plus a dagger plus a dagger a. Now let's see. Well, let me just write it once more. H bar over 2m omega and a squared n plus n A dagger squared n plus n A dagger n plus n A dagger A times n. Let's look at the first line, the matrix element of A squared. You see, A acting on n lowers n by 1. So A squared acting on n is a state proportional, is a ket proportional to n minus 2. Its overlap with the n ket, n bra, is 0. So this is basically 0. Why? You see, A squared acting on this matrix element is proportional to n minus 2. But n minus 2, they are eigenkets having different eigenvalues. So they're automatically 0. They are inner product. So the first term is 0. The second term is also 0. A dagger squared acting on n is also 0. Because a dagger squared acting on n gives me a ket, which is the n plus 2 ket, up to a proportionality constant. But the n plus 2 ket inner product with n is 0, so this is also 0. I don't need to do any calculation for those. I already know that they are 0. Let's look at the last two. Well, a dagger acting on n gives me n plus 1. But then A is acting on n plus 1, it gives me the n ket. So that third line is non-zero. Similarly, if you look at the fourth line, A acting on n gives me the n minus 1. A dagger acting on n minus 1 gives me n plus n back. So it's, in principle, that's also non-zero. But we already know that this ket, at least, this number is n. And we also know that a dagger, this was the number of n operator. This is called the number operator. It corresponds to the number of energy packs in my oscillator. And A dagger is basically A dagger A plus A dagger minus A dagger A. But you see, this is the commutator of A and A dagger, which is 1. So A dagger is nothing but the number plus 1 operator. So these two things, let's see, this matrix element is n. The third line is nothing but n plus 1. Are you following? So what we had achieved, we were looking at the matrix element of delta x squared. This is equal to, well, it's n here, n plus 1 over there. I have 2n plus 1. H bar over 2m omega multiply with 2n plus 1. This is my delta x squared, the uncertainty in delta x. Well, you see, the minimum uncertainty in delta x is obtained when n is equal to 0 in my ground state. Well, that's kind of expected if you consider the harmonic oscillator potential. If you have states that have a small energy, they will be very close to the minimum of the potential. So the spread in delta x will be small. I mean, they will not be able to move far away from the ground minimum energy. But as the energy increases, this is my harmonic oscillator potential. Ground state is somewhere over here. So typically, this is a measure of delta x squared. As the energy goes higher, well, this is now delta x. This is for 0. This is delta x squared for 1. You see, the uncertainty in energy increases as the energy of the oscillator increases. Again, keep in mind that what this uncertainty is. That is basically if you measure the position of your particle, you create multiple systems, you measure their position, so their positions will have a spread. Well, the energy eigenkets are spread all around. They are not localized at one point or the other point. That is why we had this average of x was 0. Delta x, average of delta x turns out to be non-zero, and it is the particle can spread out more distance for if its energy is larger. So that's basically what this tells me. Now let's do the same thing for delta p squared. Yes.
Hocam bu bulunabileceği aralığı belirsizliği olarak tanımladınız ya, klasik fizikte böyle belirsizlik yoktu değil mi?
Well, you see, what do we call this delta x squared? You see, in classical physics, if you would like to do this experiment, if you would like to use this definition in classical physics, so you create identical oscillators. You might have different initial values in different initial conditions. We are not specifying our initial conditions over here. If you measure their positions at arbitrary times, or you have this ensemble and you measure their positions, the average position you will find will still be 0 because some oscillators will be at the positive x, some oscillators will be at the negative x. And you will still have the same uncertainty, same spread of the observations on x. But of course, in the classical case, this delta x squared will be basically an ensemble average. You can, for example, pick one oscillator and determine its position at every time precisely. In that case, there is no uncertainty. Or you can, I don't know, maybe choose your initial conditions in such a way that all your elements on your ensemble satisfy the same initial conditions. So at a later time, whenever you measure the position, all of them will be at the same position. In classical, that would be possible to make sure that this delta x will be 0. But in quantum mechanics, even in principle, it will not be possible. Now let's look at this in the same state, p squared. Well, let me write delta p squared in the nth state. And again, we had already shown that independent of the state, this delta p squared is nothing but n p squared, average of p squared minus the average of p, the square of the average. This we had already shown that this is 0. The diagonal element of the momentum operator in the energy basis is 0. So this is equal to, well, p, if you look at the first line on the screen, p squared is nothing but minus h bar omega m over 2. Well, minus because of that I over there. And a minus a dagger squared. This is equal to minus h bar omega m over 2 and a squared plus a dagger squared minus a dagger minus a dagger a. We will just use the same argument. A squared acting on the ket n gives me the ket n plus 2. The inner product of n plus 2 with n is 0. The first term, the contribution of the first term is 0. If you look at the second term, a dagger squared acting on n gives me n plus 2 ket. The inner product of n plus 2 with n is again 0. The second term doesn't contribute. This is the number plus 1 operator. This is the number operator. So this is minus h bar omega m over 2 minus n plus 1 minus n, or h bar m omega over 2 times 2n plus 1. Now we can calculate our energy momentum uncertainty relation in the energy eigenkets. Delta p squared delta x squared This is equal to, well, delta P squared is h bar omega m over 2n plus 1. Delta x squared, we had already calculated it. It is h bar over 2m omega. Times 2n plus 1. Well, h bar omega, no, h bar no. M omegas, they cancel. This is equal to h bar squared over 4 times 2n plus 1 squared. Well, let's look at the energy for the ground state. Let's look at the ground state. What we have for the ground state.
Closed.
Yes, exactly. Still, it's a state with lowest energy uncertainty. And for excited states, the uncertainties gets larger and larger.
Daha yukarı seviyeler için h bar square divided by 4'a yaklaşan bir durum oluşuyor hocam.
Well, let's see. You see, for energy eigenkets, the product of the energy uncertainty, the uncertainties in delta x and delta p increases. That's our result. So only for the ground state, it is h bar squared over 4. For example, for the first excited state, it is 9 times h bar squared over 4. So it increases quite fast. But of course, it will be interesting to study some other states that will have this minimum uncertainty, if possible. And hopefully they will have a larger energy on the average. There definitely will not be energy eigenkets, because we see that the energy eigenkets, the uncertainty relation, the right-hand side, increases with increasing n. But maybe for some other states, they will be more like our energy eigenkets, our classical states. Now let me define one state. Alpha is some state, I don't know what yet, but it's an eigenstate of A. A is not a Hermitian operator, so alpha need not be a real number. Now, these are called coherent states. They will have some interesting properties. Now, first, let's try to calculate what are the expectation values of x and y, x and p, in these coherent eigenstates. Well, we will write down their explicit expressions, etc., but just by knowing this property would be enough to determine some of its properties. So what's the average of x in this state? Well, this is equal to square root of h bar over 2m omega alpha a plus a dagger alpha. This is square root of h bar over 2m omega alpha multiplied with a alpha plus a acting on the ket alpha dagger alpha. The first term is the a term, the second term is the a dagger term. This is equal to square root of h bar over 2m omega. Well, this is alpha times alpha. Same here. Alpha times the ket alpha. Of course, it's dagger. So this is nothing but alpha plus alpha star. The average of x in this alpha state is nothing but square root of 2h bar over m omega times the real part of alpha. Keep in mind, alpha need not be real. And for the time being, I didn't even discuss whether such states exist. I just assume that they exist. If we assume that they exist, this will be the average of x in this state. Let's look at x squared. I want to calculate the uncertainty of this state. This will be equal to h bar over 2m omega without the square root, alpha a plus a dagger squared acting on alpha. Well, we had calculated that squared before. Alpha a squared plus a dagger squared plus twice the number operator plus 1. And keep in mind that number operator is just a dagger a. This is equal to h bar over 2m omega, alpha a squared acting on alpha, plus a squared acting on alpha dagger, inner product with alpha. This is my second term. Plus twice a acting on alpha dagger multiplied with a acting on alpha plus 1. And so this is equal to h bar over 2m omega. A squared, a acting on alpha just gives me alpha every time. So the first term is nothing but alpha squared. The second term, well, the same thing, but I'm taking the dagger, so it's alpha star squared, the complex conjugate of alpha squared. The third term plus twice alpha alpha star plus 1. This is equal to h bar over 2m omega, alpha plus alpha star squared plus 1. This is equal to square root of h bar over 2m omega, alpha plus alpha star squared plus h bar over 2m omega. This is the average of x squared in this alpha state. But we had already calculated that this is nothing but the average of x in the alpha state. So the average of x squared in the alpha state is nothing but the average of x in the alpha state squared plus h bar over 2m omega, and hence the average of delta x squared in this alpha state is h bar over 2m omega. Okay, you see, when we were looking at the energy eigenkets, the delta x squared, it increased with n. But when we look at these kets, delta x squared doesn't change with n. Whatever the energy is, whatever the initial value of delta x is, it just stays the same. The uncertainty does not increase. Well, we can do the same thing for the p squared. Well, it will be an exercise for you. p squared, or let's say delta p squared in these alpha kits, they are nothing but h bar m omega over 2. Whatever the value of alpha is. The uncertainty is independent of alpha and is independent of the energy. Yeah, anyway, independent of alpha, let's say. These alpha kits are not energy eigenkits. And you see that delta x squared, uncertainty in delta x squared, uncertainty in p squared is just h bar squared over 4. So whatever the value of alpha is, these states, if they exist, we still didn't discuss the problem of their existence, if they exist, they are minimum uncertainty states for all values of alpha. Now let's also look at the energy, H. What is the average energy they have? This is just average of h bar omega times the average of a dagger A plus 1 over 2. This is h bar omega alpha squared plus 1 over 2. This is their average energy, and the uncertainty in their position and momentum do not change in time. Yes.
Harmonik osilatörün eigen state'lerini n'e bağlı bulduk.
Hı hı.
Şimdi bu genel bir eigenket tanımladık. O ne farklı oldu ki bu işte böyle?
Well,
Alfa dedik.
You see, n states, they are the eigenstates of n operator. Nope, sorry. A Hermitian operator. So this is how we define the n states. Now the alpha states, they are the eigenkets of the annihilation operator. They are different kits. Now of course, n kits form a basis. So in principle, I should be able to write these alpha kits in terms of my n kits. And if I can show that the alpha kit I can write in terms of the n kits, then I know that the alpha kits do exist. Now let's try to show it. I mean, the easiest way to prove that something exists is to build it. So that's the idea. So I will try to build this alpha kit in terms of the n kits. So let's say alpha is some coefficients multiplied by n from 0 to infinity. Let's just assume. And try to find what are these Cn's. Let's act with A on this alpha kit. So this is equal to n from 0 to infinity, Cn, A acting on n. But we already know how the A acts on n. So it lowers n by 1. And we have this square root of n in front. So A acting on the alpha kit just gives me n from 0 to infinity, Cn square root of n times n minus 1, which I can also write as n from 1 to infinity C of n minus 1. No, sorry. Okay. And from 1 to infinity Cn square root of n minus 1. Basically, the n is equal to 0 term is 0. But this is the same thing as n is from 0 to infinity Cn plus 1 square root of n plus 1 n. This is A acting on alpha. In the last line, what I did was, instead of starting from 1, I start from 0, but instead of n, I have to put n plus 1. So that the n plus 1 starts from 1 to 3, goes up to infinity. But this should be equal to n from 0 to infinity alpha times Cn acting on n. This is the definition of the alpha ket. When I act on the alpha ket by A, I should get the same alpha ket multiplied by alpha. But this equation tells me that Cn plus 1 square root of n plus 1 should be equal to alpha times Cn. So the coefficients in these expansions has to be related. Cn plus 1 is alpha over square root of n plus 1 Cn. This should be equal to alpha squared over square root of n. No, let me write it more explicitly. Alpha over square root of n plus 1, alpha over square root of n Cn minus 1. So Cn plus 1 should be equal to alpha over square root of n plus 1, alpha over square root of n, alpha over square root of n minus 1, Cn minus 2. Or up to, this should be alpha to the, well, if I continue going up to C0, alpha to the n plus 1 divided by square root of n plus 1 square root of n square root of 1. You see, if you follow the pattern, whenever n is, the difference between n plus 1 and n minus 2 is 3. If you look at that, this line over here. The difference is 3, so I have 3 factors of alpha. If the difference is n plus 1, I will end up having n plus 1 factors of alpha. That's how I know that the coefficient contains alpha to the n plus 1. And you see the Cn plus 1, the first denominator contains 1 over square root of n plus 1, the index of the left-hand side. The last one, the number is 1 larger than the index of n minus 2. So I start from n plus 1, go to an index as number that's 1 larger than my index n minus 2. Here is my last index is 0. 1 larger than 0 is 1. Or let me write it in this form. Cn plus 1 is equal to alpha to the power n plus 1 over square root of n plus 1 factorial times C0. And so I basically know what my alpha kets are. So these should be equal to C0, sum from n0 to infinity, alpha to the n plus 1, divided by square root of n plus 1 factorial. No, sorry, n. Square root of n factorial, multiply with n. So these are my alpha kets. I constructed them, so they exist. Where? Here.
En son yazdık. Evet, oradan. En alttaki şeyde summation sıfırdan başlıyor.
Okay.
Ama sonuçta bulduğumuz Cn'de n plus 1 faktörü bulduk ya.
Okay.
Orada ben sıfır koyayım mı? Biraz
Here.
evet, orada.
Well, you see, C0, I don't know what C0 is.
Evet.
C0 is over there. So this, in this expression, if you put, let's say, n is equal to 1,
En
sorry, n is equal to 0, I obtain C1 is equal to alpha C0. I don't know what C0 is, but once somebody tells me what C0 is, using C0 I can find C1. And once again somebody tells me what C0 is, I can find any Cn. That relation basically tells me that Cn is equal to alpha to the n divided by square root of n factorial C0. Now in this expression, if you want to put n is equal to 0, that expression is still correct.
Hocam alfanın değizler cinsinden varlığını göstermeye çalıştım.
Yes.
Ama en sonunda alfa içinde alfa olan bir ifadeyle.
You see, alpha is the eigenvalue.
Eigenvalue ama onun varlığını nereden biliyoruz ki?
Give me a complex number. So give me a complex number. I. You can choose I to be 0, alpha to be I. Whatever the value of alpha is, there is always a ket called alpha. You see, these kets are not discrete, they are continuous. Whatever the value of alpha is, whatever the value, there is a ket called alpha. So that is basically what we have proven. There is no restriction on the values of alpha, of the eigenvalues. Of course, now there is this problem. On one hand, we have an energy eigenbasis, which we can count, 1, 2, 3, 4, etc. On the other hand, we have these other set of bases, which basically takes this continuous complex parameter. Okay, now 2 more exercises. What is C0? Well, to determine this C0, of course, you have to normalize your state. This is 1. What if I take 2 different eigenvalues of alpha and take their inner product? It's not 0. They are not orthogonal to each other. They don't have to be. You see, they are eigenkets of a non-Hermitian operator. We have the proof that the eigenkets of a Hermitian operator that have different eigenvalues are orthogonal to each other. But this is not a Hermitian operator. So our proof doesn't apply here. Alpha and alpha prime need not be the same. No, it's not. You see, degeneracy is something else. Degeneracy is if 2 eigenkets have the same eigenvalue. Well, for each alpha, you have a single eigenket. So there is no degeneracy over here. So different eigenkets do not have the same eigenvalue in this example. So there is no degeneracy. They are not orthogonal to each other because our theorem doesn't apply here. They are not the eigenkets of a Hermitian operator. Well, this will be kind of, let's say, bonus. You see, they are not orthogonal to each other. There are too many of them, but they are still complete. In the sense that, you see, the identity, I can write the identity as a sum of these alpha kets. I should integrate over the alpha and the alpha star if I'm not wrong. And there should be some coefficients, alpha and alpha star over there. Well, you see, we are all almost all the time working on bases which are orthonormal to each other. This being normal just simplifies our life significantly. Now these kets, so-called the coherent states, they're not orthonormal. They're not orthogonal to each other. Well, you can normalize them, so they will be normal, but they're not orthogonal to each other. They are what we call an overcomplete basis. So they still form a basis. Because of this relation, you can write any ket in terms of these coherent states, but there are too many of them. Since there are too many of them, there is this function c, which kind of lowers the weight of some of these coherent states in your integral. So this is kind of the bonus. I mean, you can look up the coherent states in some other references if you like. So this is the bonus question in your homework, let's say. But these are the kets that are closest to our classical solutions. You see, we had already proven that average of x as a function of time was the expectation value of x at the time 0 times cosine omega t plus the average of p at the time t is equal to 0 over m omega times sine omega t. Now the energy eigenkets, they do not oscillate because the averages of x and p at t equal to 0, they are at 0. So they don't really correspond to oscillating expectation values. But these coherent states, one, they do correspond to these oscillating expectation values. Second, they have the minimum uncertainty. So those are the things that, let's say, that motivates us to call these coherent states as the closest we can get to the classical physics. They are quite often used in, for example, in optics, if you are interested in optics.
Neden coherent değil hocam?
I don't really know. I don't know. Probably because the uncertainty doesn't change in time.
Coherent'ın Türkçesi ne oluyor?
That I also don't know. It's coherent. Shall we give a break? Okay.
O harmonik osilatörleri kuantum mekaniğinin hangi fiziksel sistemler için kullanılıyor?
Every physical system.
Efendim?
Every physical system. You see, basically, when you actually do research, what you will see is that the only thing we can basically do is just some approximation to something we can solve. And harmonic oscillator is the thing that we can solve. So all kind of physical problems, we are kind of approximating them to harmonic oscillators. Now, it's interesting to interpret these energy packs. You see, we have solved these harmonic oscillators. So in this case, we have a single harmonic oscillator. And we have seen that the energy states, they form energy packs. So you can put 1 pack, 2 packs, 3 packs, any number of packs you want. Well, you can do basically the same treatment for 2 harmonic oscillators, not necessarily 1. So you have 1 oscillator, second oscillator, and you attach them by a spring, a coupled oscillator. Well, you can still describe these 2 oscillators, each one as having energy packs. So if you put 1 energy pack in 1 oscillator, with time, that pack can move to the second oscillator and back and forth. Or let's say you have an arbitrary number of oscillators. Each one you can still describe as energy packs, as in terms of how many energy packs they have. And these energy packs, they can start from 1 oscillator, and they can move to the other one, to the next one, to the next one, etc. So as these packs are moving around, the oscillator that takes this pack starts to oscillate faster. Its energy is increasing. So does this description sound any bells? Those that are doing condensed matter physics? No? Yeah. You have heard the word of phonons. This is what we call a phonon. These energy packs are nothing but phonons in condensed matter physics. This number operator basically counts how many phonons you have in your system. Well, here we have a single oscillator, so it's like a quantum dot. You have a the phonon can only be at a single place, at a single point, and nowhere else. Well, if you have many atoms, the phonon can just move from one atom to the other atom. And so it's used in condensed matter physics. Now let's say you have these energy packs that can move from atom to atom. Well, let's just imagine that we don't have these discrete atoms, but we imagine we have an oscillator at every point in space. There's no spacing between the atoms. So you have this energy package that can move around, that it can just go around anywhere. Well, depending on what kind of an oscillator you are talking around, this energy package that can move, that can be anywhere in space and time, you can call them an electron, a photon, a proton, or whatever you want. So we use it in particle physics. So what else is there?
Geçenlerde bir kuantum motoru yaptılar hocam, kuantum kurulma sistemi kullanarak. 2 tane artı 2 tane eşit ortasına kuantum içine bir tane atom düşüyor hocam, parçacık. Parçacık manyetik alanına etkilenerek hareket ediyor. Kendi kendine enerji üretmeye başlıyor. Ama kuantum boyutlarında.
Yeah, I had even read a news about the race of quantum nanomotors.
Yeni bir şey yani. Daha bir iki ay önce
The nano engines, they make it. But I mean, that's probably the smallest one they have. I mean, the ones that they were making the race of, I mean, they were supposed to be made up of less than 100 atoms. They're making actual races now. There were just 4 teams entering the race, but whatever physics you do, eventually what you are doing is an approximation to the harmonic oscillator. Okay, so let's give a 5-minute break. Okay, we don't have much time left anyway.